All right, so as we're looking at our introduction here to probability, I want to kind of introduce the topics from the beginning. I know some of you have studied a little bit about probability before. If you were in pre-cal honors, you guys did some. But the approach that you guys took to probability in pre-calc honors used combinations, permutations, counting principles. Those are all principles of what we call combinatorics. All right? And that is a study of probabilities that kind of is a little bit separate from statistics. We can use data and statistics within those two, but what we're going to be looking at this year is a lot more integrated with the statistics. We're going to be looking at, okay, if the mean is this and standard deviation is this, then what's the probability that someone falls within this range? Okay? Or if our chances of doing this are this, and I repeat this so many times, what's our probability of, 5 out of the 10 fitting this this characteristic? All right. So those are kind of the two areas that we'll look at as we go forward. But there are two types of probability. One is empirical, or you could say experimental, and this is an inductive approach to statistics. What we're doing in experimental probability is we're gathering data, we're trying to develop a pattern. Okay? This is the type of probability that is used throughout things like sports. Okay? The playoffs are coming up in baseball pretty soon here. So-and-so on the season has hit, 320 against left-handers. Okay? He only hits 260 against right-handers. So the opposing team, when he comes up late in the game, subs out their pitcher and puts in a right-handed pitcher. They're using probabilities there, but they're using an experimental probability because historically or inductively, this guy hits significantly better against left-handed pitchers than right-handed pitchers. So if we don't want him to get a hit, we're going to put in a right-handed pitcher. Okay? They use it in basketball. Who's the guy who throughout the season has only made like 52% of his free throws? All right, at the end of the game, that's the guy we're going to foul, not the guy who's made 90% of his free throws this year. Again, that's inductive or experimental type of probability applied in sports. And it's applied in lots of other things. If you drive a car, your car insurance is based a lot on inductive uses of probabilities, okay? If you're a guy, your insurance is going to be higher. Why? Because from experience, guys are more likely to do stupid things in vehicles. All right? If you get good grades, though, you get a discount. Why? Because
good grades, though, are less likely to do stupid things.
Okay, yeah. Typically, if you're getting good grades, you're more responsible, you're less likely to do stupid things. Okay? Once you hit 25, your insurance will go down a little bit. Why? Because once people get to about 25, they found they stop doing as many stupid things. All right? If you get married, your insurance goes down. Why? Because you now have someone to live for. Okay? And you're less likely to do foolishness. All right, so all of those things, there's an entire branch of mathematics called actuarial science. Okay, an actuary is basically a person who does math for insurance companies to try to establish rates. Okay, Miss Barheim's son does that. But that's all experimental. Theoretical is really what you guys were doing last year using the combinatorics, the permutations and combinations, or simply using a logical train of thought in order to calculate probability. We're rolling a die, there's 6 sides and there's only 1 2 on the die. So you have a 1 out of 6 chance of rolling a 2. There are 17 of you, I think. 17 of you. And, so my chances of picking your name out of a hat would be 1 in 17. That's a logical thing. That isn't, oh, we picked names out of a hat, 5,000 times, and yours came up 1 out of every 17 times. So, no, that would be experimental. Okay. Now, the experimental will typically be close to the theoretical if we've calculated the theoretical properly. Okay? If you roll a die enough times, you'll get an average of 1 out of every 6 rolls being a 2. Okay? However, you might roll it 10 times and you might get 5 2s. That's just how it happens. That's kind of the difference between theoretical and experimental as well. Okay? So then you have this idea of a sample space. And this is something you guys did talk about last year, but a sample space, that's all the possible unique outcomes. All right? All the possible unique outcomes. The number of elements in the sample space is not always the denominator of our formula for probability. Okay? So for example, if I'm rolling 2 dice, there's only one way I can roll a 2. I got to get 1 and 1. However, there are 6 different ways I could roll a 7. Okay, I could roll a 1 and 6, a 6 and a 1. Okay, a 2 and 5, a 5 and 2, a 3 and 4, or a 4 and 3. There's 6 different ways that I could roll that 7. By the way, that's why some board games, or a number of board games, have like special things happen if you roll a 7, because that's the most likely thing to roll. But the numbers 2 through 12 are our sample space. Not all of those are equally likely. All right? So there are 36 possible rolls, but only 11 unique outcomes. Okay? Does that make sense? All right. Now, probability, this is kind of a basic definition you guys have, I'm sure, seen before, but it's the ratio of times an outcome is likely to occur. You can express it as a ratio, a decimal, or percent. Please make sure as you're answering questions, if it asks you for what's the percent, make sure you give your answer as a percent. If it just says what's the probability, you can give it as any of those. But some notation here. P of E is the probability of a certain event happening. Okay, so in the case of rolling 2 dice, we might have the probability of rolling a 6. Okay, and the probability of rolling a 6 would be 1 out of 6. Okay. Now, these probabilities will always fall between 0 and 1. Okay? If you account for all the possibilities and you add up the probability of each one, that should add up to what? 1. Should add up to 1. That's actually one of the things that defines a probability distribution that we'll talk about later. Okay? So our basic formula, the probability of an event happening is the number of ways the event can occur divided by the number of possible outcomes. So again, how many ways can we roll a 6? 6. How many different rolls do we have? 36. That reduces down to 1/6. Now, here's where we get a little bit into stuff that you're going to have to deal with a lot more in SL Math. And that is combined events. All right, a union or an intersection and or, okay? This first probability formula is one that is in your formula book, but you got to make sure that you understand it, okay? It says if A and B are events in the same sample space, the probability of A or B occurring is given by the probability of A union B, union means or, and that equals the probability of A plus the probability of B minus the probability of A and B. Okay, so just a couple comments here. This means and or intersection. And this right here means or union. Okay? Now, why do we have to subtract? What do you think?
Is one or the other. So that all of those includes when both happen, versus you only have to try to find the probability of one of either A happening or B happening.
Okay, but if both happens, is A or B happening?
Yes.
Yeah, so it's okay to include that. But why would we subtract in this?
Like you would be taking out like when they happen together, like you only wanna find out the probability of them like separately and not together.
Okay, that would actually be a little bit different notation. Okay, let's look at this here. We have A and we have B. All right. This section right in here is A and B. Right? Okay. This circle is A, and we'll do this in green. This circle here is B. Now, the probability of A union B is going to be everything in both of these circles. Okay, can you guys see that? That's a little bit light. Okay, that's the A union B. So question, if I add, that might help. If I add A and B, what have I done?
You include part of the probability of A and part of the probability of B.
Okay,
Yeah.
so if I add this with this,
You're adding the same part.
You're adding some part of the same, yeah.
that's it.
Oh.
We're adding this twice. Okay? Because the intersection is included in A and the intersection is included in B. So if I just do A plus B, I've counted this middle part twice. That's why we've got to subtract this intersection to make sure we don't count it twice. Okay? Now, if A and B are mutually exclusive, that's kind of a fancy term, but it's pretty simple. Mutually exclusive events are events that cannot occur at the same time. For example, if I roll a die, I cannot roll a 2 and a 3 at the same time. Okay? It's going to land on one or the other.
Are you serious? Really?
Yeah, if I roll one die, it can't fall on two.
Oh, sorry.
Just one die. Sorry, not two dice. So, mutually exclusive, if I were drawing a Venn diagram of mutually exclusive, I would have A, and then I would have B like this. Okay? That's mutually exclusive. The intersection is empty. Or there is no intersection, you could say. Alright? Now, some of these are obvious, they're just logical. Other things, you look at the situation and you collect data and you find out that these are mutually exclusive. Okay? Think about if you had two classes that were only offered during one period, but they were offered the same time. Okay? Alright, so the set of students in the one class would be mutually exclusive to the set of students in the other class.
Us versus Dana or Jimmy.
Okay? Yeah, so then we have to get creative. Alright? But there you have two separate groups. There's no one student that's in both. Okay? Whereas with other classes, you have numerous classes where some of the students are in both classes. That would be, with an intersection. Okay, not mutually exclusive. Now, one other thing here, and there's some notation here that you need to make sure you take note of, and that is the complement principle. Now notice complement is spelled with an E in the middle, not an I. Alright, if it had an I in the middle, that just means you're saying something nice about somebody. Here you see the root. The root word here is complete. Okay? The root word is complete. So that's how you can remember how to spell it too. The idea here is that since the sample space contains all of the possible outcomes, if you add up the probability of each of those outcomes, you should get 100%, or 1. Okay? Now, we can view this one of two ways. We can view it in terms of, let's look at all the separate ones individually and add them up and get 1, or when we're talking about the complement of an event, we're talking about everything except for that one event happening. Alright, so again, going back to the dice, I could have the probability of rolling a 2, okay, which is 1 out of 6. However, I could also have a probability of not rolling a 2, which would be 5 out of 6. There's 5 other sides of the die that don't have a 2 on them. So those would be complements. Alright? Now, instead of writing not 2, you see here we use this little prime notation. We would read that if A is one of the events, then A prime is the complement, which it means that it's everything that's not A. Alright, so we have 2 or not 2. We could do it probability of 2 prime if we wanted to. Okay? And the complement principle here states that a complement will be 1 minus the probability of the event happening. Okay? So, here's a kind of a situation that you guys looked at last year. In a standard deck of 52 cards, what's the probability of getting at least 2 aces in a 5-card hand? Alright, so this was a challenging type of problem that you had to deal with, okay? So let's kind of walk our way through this one. First of all, kind of the hard way, and then using our complement, okay, which is shorter. Alright, so the long way would be, okay, so we want the probability of at least 2 aces. So that means 2 or 3, or 4, or 5, but what's the probability of getting 5 aces? 0. Okay, there aren't 5 aces in the deck. Alright? So, we'll just look at 2, 3, or 4. Okay? So, we have this going on. This is going to be, this is an OR. Alright? So this is the probability of getting 2, or the probability, so plus the probability of getting 3, plus the probability of getting all 4. Now, I can't get 2 and 3. Alright, I'm doing them individually, alright? So, the probability of getting 2 aces, there are 4 aces to choose from. I want to get 2 of them. There are 48 other cards, and I want the other 3 to be one of those other cards. So that's the probability, that's the number of ways I could get 2 aces in a hand.
It's like the stereo problem.
Okay? These are combinations. Remember those from last year?
I've never learned.
Some of them were broken.
Yeah,
We did
You
this.
guys had pre-calc honors, right?
I took calc honors.
Oh, you did calc honors.
We had one question
I've
like
never-
that. So
Okay.
we never looked. It was too bad.
No,
All right.
I've never learned that in my
Do you remember
life
it?
ever.
Well,
They're in boxes.
but let's think about this, alright? So here's the thing, combinations, we'll revisit these. We'll revisit these a little later when we get to binomial probability, but the formula for them actually is on your formula sheet, so that's kind of nice. But this is going to be out of, if we have 52 cards, we're choosing 5 of them. Okay? So that's the probability of getting exactly 2 aces. Then we have the probability of 3 aces. So again, there's 4 aces, we want to choose 3 of them. And there's 48 other cards, and we want the other 2 of the 5 to be one of those 48.
This is amazing.
So that's all over 52, choose 5. And then we do probability of getting all 4 aces. So we have 4 aces, we want all 4 of those, times, we have 48 other cards, and we only want to get one of those, all over 52, choose 5. Okay? Now, it's okay if you've forgotten how to do these or if you've never done these ones before, because the nice thing about IB is that they actually don't give you probability problems where you're using the combinations like this. That you could take entire college courses on this kind of probability. So, but anyways, that's what you would have to do in order to get the probability of at least 2 aces in a 5-card hand. Or, with a little bit less work, the probability of at least 2 aces, what would the complement of that be?
1 minus. Something.
What's the complement of it getting at least 2 aces?
getting anything but
3 cards.
Getting anything except for 2 aces.
So if we get 1 ace or 0 aces.
Alright, good. The probability of getting 0 or 1 ace. And then, but that's our complement, right?
Yeah.
So we would do 1 minus that. Okay? Now, the cool thing is that finding the probability of 0 of something is often pretty easy. Okay?
Is that the same thing as finding, like it's just another way to find the same thing?
It's another way of finding the same thing, but often it'll be less work.
I remember the first.
Okay? So
You're kidding.
we would do 1 minus. Now, the probability of 0 or 1 is the probability of 0 plus the probability of 1. Okay? So I'm going to be doing 1 minus. Now, the probability of 0 means that I want to get all 5 cards out of those other 48.
Actually,
So it's going to be 48 choose 5 over 52 choose 5. Okay? And the probability of only getting one ace is going to be 4 choose 1 times 48 choose 4. So this one we'll have to figure out, but it's still not terrible. Okay? Notice though, in this case we're only having to do 2 of these instead of 3. Okay? So it saves us a little bit of work. Alright? So this is where the complement principle can really save us some work. Now this is a very simple one as far as just a 5-card hand. But let's suppose that, we had the probability of something happening and there were 50 people. And we wanted, hey, what's the probability of at least 3 of those 50 people, experiencing this? Well, we'd have to figure out the probability of exactly 3, exactly 4, exactly 5, exactly 6, all the way up to 50.
It's not.
Okay. Yeah. It's fusion bells. All right. So you would have to figure out what would it be? 48 different probabilities and add them all together. Or you could find the probability of getting 0, 1, or 2 and subtract that from 1. Okay? So you see how it makes a huge difference in the amount of work you have to use. Now, if you wanted the probability of at least 25, then it's not going to matter. Okay?
Please don't.
You're going to have to do a lot of work
Please
regardless.
don't.
The nice thing is we'll learn how to use our calculators to do some of those
Will we be able
to save us time
use
too.
it?
You will for the ones that are complicated and stuff, yeah. Okay? All right. So that is our complement principle. All the probabilities should add up to 1. You have an event. If you want the probability of that event not happening, you just subtract it from 1. Okay? So let's practice with one of these here real quick. And I wanna just work through doing these, okay? So it says a study of the effectiveness of a flu vaccine was conducted with a sample of 500 people. Okay, so here's our 500 people. Okay? Some participants in the study were given no vaccine. Some were given 1 injection, some were given 2 injections. The result of the study are shown in the table. Okay, so they were given a vaccine, or 1 or 2, and then they either got the flu or did not get the flu. Okay? So it says a person is selected at random from the sample. Find the probability that the person selected, A, had 2 injections. Okay? So what's the probability? How many people had 2 injections? 290. Okay? So for A, 290 had 2 injections out of 500. You could just leave that as 29/50ths. If you want, you could write it as a decimal 0.58 or 58%.
Do you know that, or do you just?
Well, because 29 times 2 is 50.
I can't do that.
That's okay. If you thought about it, you could. I've been doing this a while.
I definitely do one division.
All right, so then what's the probability for B? What's the probability that someone did not get the flu?
478
Yeah, 478 out of 500. Okay, so 478 out of 500. Okay, not too hard.
Does this mean an actual question on
Like by 2.
on the exam or no? Is it going to be way harder?
It'll be a little bit more than this, but we're just getting used to it. This is intro stuff. But honestly, though, there are some questions on the exam even that are like, wait, you put that on here? Thanks. So there are some that are not
239.
terrible. Okay,
239.
239 out of 250.
I think so.
Okay. All right. Yeah, that looks good. And then finally, okay, the probability that they got the flu and had 1 injection. Okay. So how many people got the flu and had one injection?
Oh, it's really 500.
2 out of those 500. So here, look at this row. This is the people who got one injection. Okay? Here are the people who got the flu. So where do those intersect? Again, we're thinking and. All right? So that's 2 out of 500 or 1 out of 250.
Why is there more people for 2 injections?
I'm sorry, what?
Like why? No, like why are there more people for 2 injections?
Oh, I don't know.
Because it has the reverse effect.
Does it though?
Why do more people get sick if they had 2 injections than just
there were
one?
actually- there
Can
were
you really
actually-
say
I don't know.
reverse
It's just
effect?
more, there were more people who were tested with 2 injections.
Ooh,
So it's probably.
that, can you?
No, that's a good point.
Can I do my IA on giving people
There
flu
were
injections?
probably.
Yeah. Yeah?
That's a good point here, though. Like, and guys, this is why we put things in terms of these probabilities. If you just looked at the table and they're like, whoa, 13 people got 2 injections, but only 2 got the flu with 1 injection, we should just give people 1. Well, that doesn't tell the whole story, okay? Because only 54 people only had 1 injection. Almost 300 of the people had 2 injections,
It's 5% versus 4%.
okay? So 1 out of 250 is 4%?
What?
What?
Hold on. Out of the whole people.
Oh, wait, you're
I'd
saying
say like
2 out of these 54
Yeah, hold on.
got the flu, 13 out of 290 was what, 4%?
13 out of 280 was 4. They were both 4.
Okay,
It was
so
a
it's
little
about
bit.
equivalent. And that's where a researcher would say, okay, is it worth it to put people through 2 shots?
No.
You know, if we're getting the same results, whether you get 1 or 2. But guys, this is where all these probabilities, this data and stuff come into play, alright? But that's the basic gist here with probability. Here's one other one, and I want to give you guys a couple minutes here to try this one on your own. Taylor, Moore, and Perez are candidates for public office. It's estimated that Moore and Perez have about the same probability of winning, and Taylor is believed to be twice as likely to win as either of the others. Find the probability of each candidate's winning the election.
20.
I'm gonna go with it then.
Yes.
Good job.
Is it 25, 25, 50?
I don't know.
Okay.
That sounds
Hi.
alright.
I thought today was huge day because I wasn't here yesterday, so I just got.
Okay. Thanks. All right. So yeah, if Moore and Perez, if probability of Moore equals probability of Perez, okay, and the probability of Taylor is 2 times the probability of either of the others, right?
Yeah.
What are all those going to add up to?
100.
They're all going to add up to 100%, right? So probability of Moore plus probability of Perez plus probability of Taylor has to add up to 100%. But if we put it all in terms of 1, using some substitution,
Good job.
we have probability of Moore plus probability of Moore plus 2 times probability of Moore is 100%. And that's going to give us probability of Moore equaling 25%. That's good. Okay? So you could figure it out logically, you could figure it out algebraically.
I don't know why. It's just kidding.
Okay? Alright? Does that make sense?
Which situations would you use the union and the intersection?
Well, here, the union and intersection, that sort of thing, would be when you have different categories of things, and typically when there's like some overlap. Okay? Now, here we have 3 mutually exclusive events, if you think about it. We can't elect 2 different people.
Right.
Okay?
Thinking about.
So here's Moore, Perez, and Taylor. Okay? Those are three mutually exclusive events. So the union is just going to be all three of them added together. There's no intersection that we've got to subtract because we didn't count anything twice. That's really what we're using right here.
Okay.
You could say it's the probability of one of those three
Yeah.
winning.
Okay.
Okay?
Oh, that's some shit.
So.
Probability of